Turning organic material into stone is a complex process that takes millions of years to complete naturally. Certain minerals play key roles in the formation and appearance of petrified wood specimen. The petrification of organic materials gives valuable insight into the structures of natural organisms from the past. Permineralization is the process in which mineral deposits form internal casts of diseased organisms. Specific conditions must be met for petrification to occur. First, the natural process of decomposition needs to be stopped, and we do this by removing the wood sample from an oxygen source. This can happen through burial by mud, silt, or volcanic ash. The faster the tree gets removed from oxygen, the better the specimen will be produced because it doesn't have a chance to get broken down. Because petrification can reproduce the specimen structure so accurately, it's sometimes possible to determine the fossilized tree's species, age, factors about its environment, and even sometimes cell structure. The main component of petrified wood is silica. Silica, also called silicon dioxide, is composed of the two most abundant elements in the Earth's crust, silicon and oxygen. The mass of the Earth's crust is 59% silica, which serves as the main constituent of more than 95% of known rocks. Temperature, pressure, and pH also play a role in the environmental factors of petrifying wood because wood's organic material cannot withstand temperatures that are too high or pressures that are too high, and wood chemically breaks down at pH levels lower than 4.5 and higher than 7. So silica, the main component of petrified wood, has three main crystalline varieties: quartz, tridymite, and cristobalite. Silicates all contain the same fundamental atomic structure of the tetrahedron, in which one silicon atom is surrounded by 4 equally spaced oxygen atoms. Silica molecules bind in an array of different structures, including single chain peroxenes, double chains that form needle-like crystals, mica sheets, tectosilicate feldspars, and the diamond-like framework of quartz. The highly organized atomic structure of quartz means that petrified wood samples are going to be between a 7 and 8 on most hardness scale. For reference, talc or chalk rates 1 and diamonds are a 10. So it's a pretty hard structure that can withstand quite a bit of environmental factors. Petrified wood is observed in a variety of different colors. In silica-based structures, common trace minerals that affect color are going to be transition metals or elements 21 through 29. We see this specifically with these elements because they have partially filled d orbitals. Electrons transitioning between positions in the d orbital absorb energy in the visible light spectrum. To help explain the different coloration and reasons why behind petrified wood samples, I will be referring to a study done by the geology department at Western Washington University. They used LAICP MS spectrometry to reveal how the presence of trace minerals determines the rainbow of colors that we can see in petrified wood samples. So the overall conclusion that this study had explaining the colors of petrified wood was that most specimens were affected mostly by iron. So this is because iron can occur in various oxidation states, which naturally range from browns to greens to reds. In specific green pieces, we less commonly also see the addition of other trace metals such as chromium, tin, or manganese. And in certain red pieces, we sometimes observe the addition of uranium. In pieces that are black, white, or clear, this study found very low levels of any trace elements. The white coloration is often observed because of microscopic fluid inclusions within the silica. And the black coloration may simply be caused by the low reflectance of translucent chalcedony. While brown is the most common color observed in petrified woods, the Western Washington University found brown pieces actually showed the greatest variation in trace elements. They reported traces of copper, vanadium, and tin to be other major elements found. There are pieces of petrified wood, so let's step back a bit. There are pieces of petrified wood that do show a variety of different colors, as shown in this picture. This is informally known as rainbow wood. George Mustow, a retired professor, current research associate at the Western Washington University, and the author of my referred to color study, explained that the, quote, complex color patterns result from progressive nature of the fossilization process, which causes wood to have varying degrees of permeability during successive episodes of permineralization. But the study did find that iron was the main component in most of all of these colors, just as seen in samples that were one solid color. So recently, scientists in Washington have been able to artificially create petrified wood specimen. This process still needs refining, but the hope is that research can refine the results of this process and obtain a sample of mineralized wood with specific pore size and patterns so it can be used industrially. Potential applications might be separating industrial chemicals, filtering out pollutants, and soaking up contamination. Specific conditions must align to form solid rock from the mold of a diseased tree. These rocks, often composed of silicon quartz structures, come in an array of varying shapes, sizes, and colors. The complex process holds potential industrial use for us in the future. Overall, the process of petrification yields stunning replicas of trees that grew on our Earth millions of years ago.